We are continuing with Rao Bhim book, section 7.2. Example 7.2.6. This example looks rather scary. It talks about vector space of all random variables with mean 0 and finite variance defined on a fixed probability space. Indeed, it is beyond our scope to deal with this example in its full generality. Instead, we shall consider a particular case which will explain the main idea. The example talks about a probability space. This concept is related to the concept of a random experiment, that is, any activity whose outcome depends on chance. For example, rolling a die. The possible outcomes here are 1, 2, 3, 4, 5 and 6. Now each of these things occur with some probability that I will call, say, P1, P2, P3, P4, P5 and P6. For instance, all of them may be just 1/6. Now using this, we can define or compute the probability of any event, that is, any subset of this set. Say for example, I want to find out the probability that my die is going to show some even number. Then this probability of even will be just obtained by adding all the even things, that is P2 plus P4 plus P6. So in this way, whenever I have a random experiment, then the set of all possible outcomes together with a probability assignment to compute probability for any event, that is called a probability space. So that is the first concept that we need to understand. Now the second concept is the concept of a random variable. A random variable is just a function defined on the probability space, this set 2R. So in our example, any random variable is basically a function like this. Now any such function can be identified completely by these 6 numbers f1 to f6. So I can consider a function as a 6 tuple, and as a result the set of all my random variables in this example is nothing but R6, which is a vector space. Now that is not the vector space that we are talking about here. We are putting some further restrictions, mean 0 and finite variance. So let's understand what is meant by mean. Here mean is defined as this number. Whenever you have some random variable f, I take all the values, multiply them with pi and I add, that is called the mean. I am not going to discuss what is the intuitive interpretation of this for this particular example. Similarly, variance is defined as this complicated looking thing. I square each of my fi's, multiply that with p and add them, and then from it I subtract basically square of this quantity. So that is the definition of mean and that is the definition of variance. Now in my example, we are working with all those random variables, that is all those f, which satisfy the additional condition that this is equal to 0 and this is finite. Now since our sums are all finite because our probability space is finite, so clearly this is bound to be finite. So the condition of finite variance holds here trivially. That really does not rule out any of my random variables. However, this is a non-trivial condition, so the final vector space that we are working with becomes B equal to all those elements in R6 such that they satisfy summation pi xi equal to 0. So what I earlier called f of 1, f of 2, I am just calling them x1, x2 up to x6 to keep similarity with our regular notation. Now the book claims that covariance, something called covariance, is an inner product on this vector space. So let us understand what covariance is. As this is going to be a candidate for being an inner product, so naturally it should combine two such things. So I will call them, say, f and g, two of my random variables, and combine them into a single number. And this is the definition. What you do is you multiply fi and gi together, multiply it with pi and add. From this you subtract the mean of f times the mean of g. Fortunately for our example, I am assuming that we are already in this space, so f and g are both in this space. As a result, their means are anyway 0, so this part is just not there. So we are left with the simple definition: covariance of two elements of this vector space is summation pi fi gi. And using a more familiar notation, we have covariance xy, x vector, y vector, equal to summation pi xi yi. Just remember that all the pi's are greater than or equal to 0 because they denote probabilities. Now the claim is that this is going to be an inner product. So we have to check the three conditions. It is very easy to see that if I swap x and y, this will not change. The first condition is trivially satisfied. If you take any linear combination in place of x, it is going to split up nicely because we are just doing ordinary multiplication and addition. The third condition will give us some trouble. And the third condition is, if covariance x with itself is computed, then that must be a non-negative real number, which is very easy because you will get xi squares which are non-negative, pi's being non-negative, product sum, etc. also non-negative. This part is just fine. Now suppose this happens to be equal to 0. From this I have to show that all the xi's must be equal to 0, and there I will run into a little problem because all these quantities being non-negative, their sum equal to 0 means for all I, pi xi square is equal to 0, but that does not mean that xi's are equal to 0. It is quite possible that pi's are equal to 0. So if someone tells me that all the pi's are strictly positive, then I immediately get this. But it might be the case for a general setup where some pi is equal to 0. So let's quickly take a look at one such example. In various gambling houses, we meet dice that are not fair. So what they do is that they do some kind of mechanism inside it such that it will never show up 6. Not just low probability of 6, 6 is just impossible. There is a face called 6, but it will never land on it, possibly some kind of a magnet, etc. set inside. As a result, you will have P6 is equal to 0, and to fix up ideas, suppose I assume that all the other faces have equal probability, 1/5 each. Now in this case, if I am trying to compute that quantity covariance x with x, I am going to get covariance xx is 1/5 of sum of squares of all the xi's from 1 to 5. x6 doesn't enter into the picture at all because that gets multiplied with P6, which is 0. Now if I tell you that this is equal to 0, you can immediately conclude that x1 to x5 must be equal to 0. x6 you have no control on. x6 can be just anything. So covariance xx is equal to 0 does not imply that x is the 0 vector. But then the question is, do you really care? So if you know that your die is never going to show the face 6, who cares what happens with x6, because you are never going to have that particular outcome. So you might as well say ignore that. So if you say ignore that, in that case you really can say that after that ignoring, covariance of x and y is really like an inner product. Now this ignoring will require a little bit of mathematical working in general, but for our example the ignoring simply means instead of working with R6, you restrict your attention to only R5, that is x1 to x5, and say don't care about x6. In that case, all your vectors are now members of R5 and your covariance function is defined on R5 cross R5 to R, and then it is a valid inner product. So this is basically the main idea in that particular example. Now, that example doesn't work with only this particular probability space. They are working with a general thing, and for that, the same argument holds, except that we have to have more sophisticated mathematical machinery to define mean, variance, and covariance. But otherwise, the main idea is exactly what I said here.